The topic of the speed of light has been debated for many centuries and even millennia, until it was finally put to rest by Danish astronomer Ole Romer in 1676. Before this, key historical figures had all sorts of ideas about how light travelled. Empedocles, for example, believed that light did travel at a finite velocity, but he didn't have any experimental evidence for it. Aristotle, on the other hand, disagreed. In his book Sense and Sensibilia, he said that light is due to the presence of something, but it is not a movement. Since speed is defined as a movement over a set period of time, the argument for a finite speed is pretty easily dismissed. Of course, this discourse happened over 2,000 years ago, and in more recent times, the great French philosopher and mathematician René Descartes posited experimental proof for an infinite velocity of light, in response to an experiment done by Beekman in 1629. Galileo's idea to measure the speed of light was to have two lantern bearers standing a known distance apart. Once the first lantern bearer uncovered their lantern, the second would immediately uncover theirs as soon as he saw the light. Galileo tried this with an assistant across many miles, but naturally could not make out any time delay and only came to the conclusion that light is at least 10 times faster than sound. Everything changed when Romer got involved, but he wasn't even trying to measure the speed of light. During his time, the technology required to accurately determine the time at longitude 0 did not and would not exist until British horologist John Harrison developed his chronometer in 1761. Romer was going off of Galileo's suggestion that the tables of the orbital motion of Jupiter's moons could provide a clock in the sky, with each individual eclipse representing the tick of a hand. Navigators and map makers anywhere could use this clock to read the standard time at a place of known longitude, like the Paris Observatory where Romer was working at. Romer decided to focus on the moon Io as it was the closest to Jupiter and therefore had the smallest period, known now to be 1.769 Earth days. An eclipse happened every orbit, which Romer timed for several years. However, he noticed something unexpected. As Earth moved closer to Jupiter in its orbit, the time interval between consecutive eclipses became shorter, and it became longer as Earth moved further away from Jupiter. He realized that this would make sense if light had a finite velocity, as it would have to cover extra distance in order to reach Earth from Jupiter when it was on the other side of the Sun. After all, sunlight reflecting off of Io's surface is what allowed Romer to make his observations in the first place. Based on the accumulation of the time differences, Romer was able to estimate that the eclipse would occur 11 minutes before it was predicted when Earth was at its closest to Jupiter, and 11 minutes after it was predicted when Earth was furthest away from Jupiter. All that was left to do was to take this extra distance equal to the orbital diameter of the Earth, or twice the astronomical unit, and divide it by 22 minutes. This arithmetic was not carried out by Romer, but rather a Dutch physicist by the name of Christian Huygens. His calculation yielded a value equal to 131,000 miles per second, which is about 70% of the true value. This 30% difference was because of some errors with Romer's estimation of the maximum time delay, which should have been 16.7 minutes rather than 22, along with the inexact knowledge of the astronomical unit, which we now know to be exactly 149,597,870,700 meters. But what matters is that this was the first quantitative measurement of the speed of light that was not too far off from the true value and conclusive evidence that it is indeed finite. The true value of the speed of light has been used to define the standard unit of length, the meter, as the distance a photon can travel in exactly 1,299,792,458th of a second. The experiment is reproducible and can be carried out by anyone as technology has improved vastly since Romer's time. And the arithmetic isn't very difficult at all, especially now that we have calculators. High-quality telescopes can be purchased anywhere for very little, but the most difficult part would probably be replicating his sheer dedication to the project, collecting data for years. Although it didn't help any navigators at sea due to the motion of the boat being magnified tremendously by any telescope which could only view a small patch of the sky regardless, it did however prove to be useful in determining the longitude of islands and ports while on land, and of course ended a debate that spanned across millennia. And for that, Ole Romer will always go down as a revolutionary figure in the world of physics, setting down a huge stepping stone for his successors. Although it wasn't his calculation, it was his data that was used. Data that he'd collected relentlessly for years. And his brilliant insight as an astronomer that allowed him to recognize that the delays weren't because of some cosmological phenomenon, but rather the finite speed of light.